Welcome to networks. Let's jump right into it. So undirected graphs. A graph is a diagram which shows connections or pathways between people, places, and objects. We're going to have to learn some key definitions here, and we'll be referring to this network right here as we do so. The first thing, a vertex, or the plural vertices. Point or points on the graph. So in this network right here, this is referring to A, B, C, D, and E. They represent entities such as people, places, or objects. So all of these dots here are what we refer to as a vertex, or the plural is vertices. So all of these dots here, A, B, C, D, E, are known as vertices. Next is an edge. An edge is a line joining two vertices, represents a connection between the vertices. So all of these lines here that are connecting my vertices together are known as edges. Next, adjacent vertices. So these are vertices joined directly by an edge, e.g. vertices A and B. So if we look up here, we have A and B, which is joined directly by this edge. Adjacent just means they're next to each other. So A and B would be referred to as adjacent vertices. Next, an isolated vertex. So an isolated vertex is a vertex without a connection to any other vertices, e.g. vertex E. So as you can see here, there are no connections from E to any other vertex, so we refer to E as an isolated vertex. Next one, multiple/duplicate edges. So where two or more edges join the same two vertices, e.g. edges between C and D. So the way I like to think about this is that there are multiple routes from one vertex to another. So if I start at C, I could go this way to get D, or if I started at C, I could go this way to get to D. So that means it is has multiple edges or duplicate edges. Next, a loop. Let's highlight it. What is a loop? This one is pretty self-explanatory. A loop is an edge that connects a vertex to itself, e.g. vertex A. So if we come up here, A has this edge that connects it back to itself, so we refer to this as a loop. Now, an important line here is that, note, a loop counts as degree of 2, but only counts for 1 in an adjacency matrix. We'll see an adjacency matrix in another lesson, but we are going to talk about degrees very soon, and that time is now. Look, degrees. Okay, a degree of a vertex. The number of edges attached to a vertex. So that's what a degree of a vertex is, the number of edges attached to a vertex. So let's come up here and let's really analyze this. So let's count the degree of each vertex. So would you agree that there are 2 edges attached to vertex B? So that has a degree of 2. For this one, we have 1, 2, 3. This has degree 3. This has 1, 2, 2. Now, for this loop here, if we come back to our definition of a loop, it says a loop counts as degree 2. So that means that and that. So just this loop section, I have a degree of 2 because this and this counts as 2 separate degrees. And then for this one, we also have that one there. So that means 3. 3 degree for A. And for E, we have 0. Okay, let's keep on going. Some other cool things here is this. So the sum of all the degrees of all vertices is equal to 2 times the number of edges in the graph. So let's begin by taking the sum of the degrees of all vertices. So that means I add them all up. So what I'm going to do is I'm going to find sum of all, I'll write it exactly, sum of all degrees of vertices. I'll just say sum of all degrees. 3 plus 2 is 5, plus 3 is 8, plus 2 is 10, and then 0 does nothing, so 10. So the sum of all the degrees here is 10. And what this is saying is that 10 is going to be equal to 2 times the number of edges in the graph. Well, let's come up here and count the number of edges I have. 1, 2, 3, 4, 5. What is 2 times 5? 2 times 5 is 10. So this is a true statement right here. The sum of the degrees of all the vertices is equal to 2 times the number of edges in the graph. The other cool thing that we can say here is that the sum of the degree of all in a graph vertices is always even. I can't read this sentence for some reason. The sum of the degree of all in a graph vertices is always even. So to put it simply, if you add up the amount of degrees in a graph, it's always going to be even. And you can see that right here. The sum of all the degrees here was 10, and 10 is an even number. Let's look at a couple other examples here just to further prove this to ourselves. If I drew this, So they are my two vertices, and I drew an edge connecting them. Well, you would say this has a degree of 1, this has a degree of 1, 1 plus 1 is 2. What if I was to draw another type of network here? What if I was to draw this with 3? Boop, boop, boop. All right, then we'll come here. This has a degree of 2 because I've got 1 coming out there, 1 coming out there, 2, 2, 2. 2 plus 2 is 4 plus 2 is 6. So as you can see, and hopefully this is a very rough proof, but the sum of all the degrees of a graph is always going to be even. It also says here, refer to the degrees of a vertex when asked to find Euler's trails and circuits. We'll see that later on. Example 1, state the degree of each of the vertices shown in the graph above. We've already done that. So up here, we drew it all in. We showed the degree of each vertices shown in the graph above, and we also proved these statements to ourselves. Okay, hopefully this was a good little introduction to networks here, and I'll see you in the next one.